Well, hi there, sports fans. Welcome to another exciting episode of Physics 12, which is lesson 2.8 today. And we're going to look at a couple of other two-dimensional force problems. And we'll see how we deal with these specific kinds of problems. And the first one is what we call the boat problem, for obvious reasons. And so here what we have in this scenario is we have two people on either side of a canal here that are pulling a boat down the canal with some ropes, and they're each pulling at a certain angle and pulling with a certain force, and we want to determine what is the net force on the boat. So we'll work through that and see how we deal with that kind of a problem. So first of all, what we're looking for is we're looking for the components of each of these forces in the x and the y direction, and then when we get those, then we can add the forces in the x component together and then add the forces in the y component together, put them together, and then find out what our resultant force is. So let's see how we do that. All right, so I've got our components down here now, and as you can see, we've got, so we're looking for the y component of A, we're looking for the x component of A, and then we're looking for the y component of B, and then we're looking for the x component of force B. So we'll start out with force A in the x direction, and so that's going to be this one here, Fax, and that's going to be the magnitude of force A times the cos of 45 degrees. So our angle is 45 degrees here, and being is that we want this component, that's going to be the cosine ratio that's going to give us that. And so that will then be 40, which is the magnitude of force A times the cos of 45, which is 0.707. So this force, this component here, then will be 28.3 newtons. All right, so now let's find out what the y component of force A is. And in this case, the angle is still 45 degrees, but now we need the sine ratio in order to find the y component of force A over here. So we just go once again 40.0 times 0.707. The sine of 45 is the same as the cos of 45, so these happen to be the same, 28.3 newtons. So we'll put them on our component diagram right over here. So we have now we have the components of force A, and then we can go ahead and find the components of force B. So force B in the x direction first. Again, that's going to be, our angle now is 37 degrees, and force B is 30 newtons. And now we need the cos of 37 degrees, because it's the x component that we're looking for, so it's the cosine ratio that we need. And so that would be then 30.0 times the cos of 37 degrees, which is 0.799. And we get 24.0 newtons. So that's the x component of force B. Now the y component of force B, that's going to be, we need the sine ratio now. So it'll be the magnitude of force B times the sine of 37 degrees. And so that'll be 30.0 times 0.602. And we get 18.1 newtons for the y component of force B. So we can put those values on here. So we have all of our components, the values of all the components here now, and so now we can go ahead and find out what the resultant force is going to be. So here's a diagram of what the resultant force would approximately look like, and then we can put the numbers in there. And so the resultant x component of the force will be the x component of force A plus the x component of force B. So that would be this one plus this one. And we put the numbers in. So 28.3 plus 24, that gives us 52.3 newtons. So that would be this one right here. And so we can put that on there. And now we need the y component of our resultant force. And that is going to be the A component, or sorry, the y component of force A plus the y component of force B. And as we recall, the y component of force B is a negative number. And so I don't know if I mentioned that earlier, but we do get a negative number for the y component of force B, so we end up subtracting them. So therefore, the net force in the y direction is going to be 10.2 newtons. Okay, and then we can put that on our diagram there. And then it's just a simple matter of using Pythagorean theorem plus the inverse tan now to find the magnitude and direction of our final force. So the final force then is going to be the square root of 52.3 squared plus 10.2 squared, just your basic Pythagorean theorem. So the magnitude of a resultant force then is 53.3 newtons. And to find the angle then, it'll be the inverse tan of 10.2 divided by 52.3, and that gives us 11.0 degrees. So to express our final resultant force on the boat in polar form, that would look like this. So the resultant force is 53.3 newtons at 11.0 degrees north of east. So that would be, that's how, again, how you want to express your final answer in polar form like so. So quite a few steps on here, but really, once again, if you break it down into your x and y directions and make sure your diagram is good, you have a good diagram for all your forces, then that really helps you in dealing with this kind of problem. So we'll have one other type of problem that we'll look at, and we're just going to introduce the concept of static equilibrium. We will be looking at this quite a bit more in the future, but we'll start out with a fairly simple example of static equilibrium at this time. And what we mean by static equilibrium is simply that the forces are balanced in both the x and the y direction. When that situation occurs, then that means that your object is in static equilibrium. So you have balanced forces in the x direction, and you have balanced forces in the y direction. And this is a typical kind of a problem right here, where we have some object that's hanging straight down like so, and you have two sort of cables that are holding it in place, and you want to find out what the forces are on those particular cables. And so what we need to do is we want to find out what is force A and what is force B. And so the way we do that is we write balanced force equations in the x and the y direction. Well, that's pretty easy for force B because it's only in the x direction. But force A is going to have two components, and so you need to make sure that you're aware of that. So you can see force A will have a component in the x direction, and it will have a component in the y direction. So let's look at the y direction here first, so in the vertical. And force B is not a factor in this, and so we don't need to worry about force B. We just need the y component of force A. So the y component of force A then will actually equal the weight of this chandelier, which is 1960 newtons. And so that's where we can start. So the y component of force A times the sine of this angle here, which is 60 degrees, that has to equal the weight of the chandelier. So there's your balanced force equation in the y direction right there. So that'll give us force A relatively quickly, because force A is just simply 1960 divided by the sine of 60 degrees, and we end up getting 2260 newtons. All right, so we have the magnitude of force A now, and so now we need to go back in the x direction to find out what force B is. And the way that we will do that is we will use the x component of A, and the x component of A has to equal the force of B, because B is in the x direction only, and so this component, the x component of A, then will have to equal force B. Well, we know already what force A is. Now we just need its x component, and that's going to be the magnitude of force A times the cos of 60 now to give us the x component. So the x component is Fa cos 60, and that'll have to equal force B. Again, it's a fairly simple calculation now because we had the magnitude of force A, which we found earlier, and now just times the cos of 60 equals force B. And so you just do that calculation and you'll get 1130 newtons. And so, here's a fairly simple, straightforward, static equilibrium kind of a problem. We needed to find the magnitude of both these forces, and that's what we've done. The magnitude of force A is 2260 newtons, and the magnitude of force B is 1130 newtons. And when those forces are of that magnitude, then you will have static equilibrium in this kind of situation. And as I said, we will be dealing with more problems like this with static equilibrium in the future. We just wanted to introduce the concept at this time.